And so in 3.2.1, we found that the speed at which ball A is going to hit the ground is actually 12.52 meters per second. And now in the next question, which is 3.2.2, they are asking us to calculate the speed at which ball B was thrown downwards. And so basically they are asking us to find this initial velocity, which we had noted when we were analyzing our question. And of course, as we had already noted, the only information that we have regarding ball B is its change in position since it was thrown from the same height as ball A. And of course, its acceleration is going to be g. We also know that it was thrown after 0.6 seconds relative to ball A, but they both reached the ground with ball A at the same time. So let's see if this information is sufficient for us to solve this question. And we can start by consulting our formula sheet and go to the equations of motion. And so if we look into the first equation, we see that we might be able to use it to find the initial velocity. But in order to do so, we would need to have the final velocity as well as the change in time for our projectile. But unfortunately for ball B, we do not have both of these quantities. So perhaps it's not the best option for us to go with. So let's see the second equation. In the second equation as well, we see that we might be able to use it to find the initial velocity. And in this case, we would need to have the change in position as well as the change in time for our projectile, which is ball B. And fortunately, at least this one is better because for ball B, as we had already discussed, indeed we do have the change in position, but we still do not have the change in time. But this is obviously a much better option compared to the first equation. And perhaps we can actually use the information we have and solve for the change in time of ball B so that we can then be able to use this equation to find its initial velocity. And so let's see if we have got enough information to do that. So if we are looking at the information regarding ball B alone, all we know is that it was thrown 0.6 seconds after ball A, but they both reached the ground at the same time. So this is actually a clue which we can use to link the change in time of ball A to the change in time of ball B. Because if we are looking at the quantities that we know for ball B alone, they are still not enough for us to solve even for the change in time. But for ball A, we have got enough information to know its change in time. And then we can use this information about the initial time of ball B as well as the fact that they both hit the ground at the same time in order to relate the change in time of ball A to the change in time of ball B. And that is exactly what we are going to do. And so our first step in solving 3.2.2 will be to calculate the change in time of ball A when it reaches the ground. And so we are again going to go back to our equations of motion. And if we look into the first equation again, for ball A, we can actually use this equation to work out the change in time because we do have the final velocity for ball A, which we calculated in the previous question. And we also know what the initial velocity was for ball A. And of course, the acceleration is just g. So this is great because we can now use this equation to calculate the change in time of ball A when it reaches the ground. And that is going to be our first step in solving 3.2.2. So let's go ahead and do that. And so in 3.2.2, the first thing that we are going to calculate is going to be the change in time for ball A. And as usual, the first thing that we need to do is to indicate our positive direction. And since we had already used in the previous calculation downward as our positive direction, we must remain consistent with that direction throughout the rest of the questions. So downward is still going to be our positive direction. And then the formula that we are going to use is VF is equal to VI plus G delta T. And so since we are interested in finding the change in time, we can actually make it the subject of the formula even before we substitute the rest of the quantities. And so we will get that the change in time is going to be equal to the final velocity minus the initial velocity divided by the gravitational acceleration. And then we can substitute in the quantities. In the previous question, we found that the final velocity of ball A is 12.52 meters per second. And of course, the initial velocity is just 0, so we can actually just scratch that one out because it's nothing. And the gravitational acceleration is always 9.8 meters per second squared. And then using your calculator, you will find that the change in time is going to be 12.52 divided by 9.8, which is equal to 1.28 seconds. So this is the amount of time that ball A is going to take to reach the ground. And again, you will actually notice that this is a calculation that is exactly the same as the calculation that we did for the projectile in the November 2016 paper, the second calculation that we did there. So let's now see how can we use that in order to find the change in time for ball B. And so again, we were told that ball B was thrown after 0.6 seconds relative to ball A. And secondly, they told us that both of these balls are going to reach the ground at the same time. So that is very important because it gives us a clue on how we can link the change in time of ball A to the change in time of ball B. And so basically, this information is telling us that ball B is actually going to take 0.6 seconds less to get to the ground compared to ball A, meaning that the change in time for ball B is going to be equal to the change in time for ball A minus the initial time or the starting time of ball B, that is the 0.6 seconds. Okay, but if you are not 100% convinced, we can actually also prove this mathematically. So here is how. This is the change in time for ball A. And we know that the delta T, or the change in time of A, is equal to the time final of ball A minus the time initial of ball A. And so we now know that this change in time for ball A is 1.28 seconds. we do not know what the final time is when it reaches the ground, but we do know that the initial time for ball A was 0 seconds. And so therefore, the time final for ball A is equal to 1,28 seconds. Okay? And now this is important because we know that ball A and ball B reached the ground at the same time, which meant that the time final for ball A is equal to the time final for ball B. So this 1,28 seconds is also going to be equal to the final time for ball B. Okay? And so now we can do a similar calculation for ball B, but with the aim of finding the change in time. So that is going to be equal to delta t of B. And we know that this is going to be given by the final time of ball B minus the initial time for ball B. Okay? And we do know that the final time of ball B is actually also equal to 1,28 seconds. And we also know that the initial time of ball B is 0,6 seconds. And so 1,28 seconds minus 0,6 seconds is going to give us the change in time of ball B, which is going to be 1,28 minus 0,6, that is equal to 0,68 seconds. And so that is going to be our change in time for ball B. Okay, and now this is great because we now also know the change in time of ball B, and we can then use the second equation of motion in order to calculate its initial velocity. Okay, and so for the final step of this question, we are now going to take the second equation of motion. We now do have the change in time, meaning that we have got enough information to find the initial velocity of ball B. So for the final step of 3.2.2, we are still taking downwards as our positive direction, and we are going to use the equation delta y is equal to vi delta t plus half g delta t squared, right? And all we want is to find the initial velocity. And so we can say that this initial velocity is going to be given by delta y minus half of g multiplied by delta t squared, all divided by delta t. And so I have just made vi the subject of the formula, and then we can substitute all these quantities. We know that delta y is 8 meters. So minus half multiplied by g, which is 9,8, and now multiplied by our delta t squared, which we have calculated and found that it's 0,68 seconds for ball B. And so we write 0,68 seconds squared. And then we divide by delta t, which is 0,68 seconds. And that should give us the initial velocity of ball B. And of course, for using your calculator, you will find that 8 minus 1 over 2 multiplied by 9,8 multiplied by 0,68 squared divided by 0,68 is equal to 8,43 meters per second. Okay, and so that is going to be the magnitude of the initial velocity of ball B. Wow, what an interesting question. So in order to solve 3.2.2, we needed to start by calculating the change in time for ball A. We then used the information that we were given to relate that to the change in time of ball B. And so finally, we had enough information for ball B in order to find its initial velocity. And we just used the second equation of motion to do that. And then we found the initial velocity of ball B. So I think this was quite a very interesting question. And I hope that you enjoyed the video and hopefully learned something from it. And I think one of the important things that this question is showing us is that the key in mastering these questions is to start by reading the statement carefully with understanding and take note of all the keywords or key information that they have used in the question, because they are going to give you the clues that are going to help you in answering the question.